All right. Okay, chemistry 3111. Another cool reaction is what's called reductive amination. This is a very popular reaction with chemists nowadays, and because it works really, really well, and as we alluded to today, there's many, many drugs that possess amines in them. And so chemists who are trying to develop new drugs are always looking for new and exciting ways to make amines. Always looking for new ways to make amines. And so reductive amination is nothing more than a good way to make primary amines, secondary amines, and tertiary amines. So let me show you how you make or how you perform a reductive amination. So what you do is you start with a ketone or aldehyde, and you can convert that into an imine. Now we talked about imine synthesis a lot earlier on in this class, so everybody knows that you would take your ketone or aldehyde, treat it with a catalytic amount of acid in your amine. In this case, we're using ammonia, and here you end up with your imine, right? We talked about imines and enamines quite a bit earlier on in the book or in the class. And so to reduce that, it says you can use a reducing agent like hydrogenation conditions, just hydrogen and palladium, platinum, or nickel, and you can make a primary amine, like as is shown here. But it says that if the reducing agent is present, the amine can be reduced in situ to form an amine. So in situ, all that means is in the same flask. So in the same reaction flask or vessel, whatever you want to call it. Okay, so there is a way that you can do reductive amination, and you can do it all in one step. You can basically go from here to here directly, and that's what in situ means. It means you do it all at one time. And so there's a lot of reagents that we can use to do reductive amination, but it's here sodium cyanoborohydride, which is similar to sodium borohydride, is commonly used. Why? Because it's so selective for imines, sodium cyanoborohydride. We abbreviate it like this, NaBH3CN, like that. And so sodium cyanoborohydride, the only difference between it and sodium borohydride is you just replace one of the hydrogens with a cyano group, which is electron withdrawing, and it mitigates or lessens the reactivity of the borohydride because it stabilizes the negative charge, rendering it again more selective. So essentially, what happens is this: the sodium cyanoborohydride will not react with an aldehyde or a ketone. Okay, but once the imine is formed, it will reduce that. So it will reduce an imine, but it won't reduce an aldehyde or a ketone. So how do you put it all together? You do it like this. Whether you want to make a primary, secondary, or tertiary amine, you would take your ketone or aldehyde, treat it with your amine, catalytic amount of acid, and sodium cyanoborohydride, and everything occurs in situ, all in the same reaction flask. Okay? These combine to make your imine, but then once the imine is formed, remember, this isn't going to attack the starting material, but as soon as the imine is formed, it's going to reduce it to make a primary amine. If you use a primary amine, then you're going to end up with a secondary amine after your reductive amination. And if you start with a secondary amine, then you make a tertiary amine. So a very powerful reaction, reductive amination, right? All you need is an amine, a little bit of acid, and sodium cyanoborohydride, which isn't a very expensive reagent. So you can see why this is so popular with organic chemists. Now, question 22.14 says, show two different ways of preparing each of the following compounds via a reductive amination. Well, I'll see about preparing each one by two different ways, but let's start with B. Right, you've got two propyl groups, and you've also got a methyl group. I mean, you could cleave either one of these, but we'll start by cleaving this here. So what does that mean? That means that if we were to start with these three carbons on an aldehyde, like this, if we started with this aldehyde, so I'll write it like this. This is propionaldehyde. If we were to treat that with this amine, so this is methylpropylamine, like this. There's our methylpropylamine. We want to treat it with that, a catalytic amount of acid, and sodium sodium cyanoborohydride, that's going to give us the desired product. Now, there is another cleavage that we could do. If we were to break this bond right here, this one, the methyl, then what would the aldehyde look like that we're going to start with? We would actually start with formaldehyde, right? You'd start with this aldehyde, only one carbon. Then you would treat it with the dipropylamine. So 1, 2, 3, nitrogen, hydrogen, 1, 2, 3, like that. A catalytic amount of acid and sodium cyanoborohydride. And that would also give you the product. Okay? We can do the exact same thing in the next one. We could either cleave the nitrogen carbon bond here, or we could cleave the nitrogen carbon bond there. Either way, we're going to end up with the right product. Okay, I'm going to try it just by cleaving the one in red. Okay, if we were to break that, what would you end up with? You end up with a compound that has both the ketone. So your ketone would look like this. You have 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6 carbons, followed by your amine. Did I have too many carbons? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. No, I just noticed that I made a mistake on my answer in my thing here. So 1, 2, 3, 4, 5. 2, 3, 4, 5, 6, and then I have NH2 here like that. There you go. So that's going to be your starting material, but you've got the ketone and the primary amine in the same molecule. So this is an intramolecular reductive amination. So all you'd have to do in this case is take the molecule and treat it with a catalytic amount of acid and sodium cyanoborohydride, and that is going to give you the product. Okay. Again, you could break this bond too. Okay, you could break that one too, and you could try doing that one on your own. So let me see here. Let me divide this up a little bit. Okay. And in the interest of time, we're not going to do everything, but I just want to try this one here, the last one. Let's say you were to break this bond right here. And again, you could break that one, or you could break this one. Either way is going to work. Okay. And I encourage you to try them both. But if you were to break this bond right here, what would you end up with? Your starting material would look like this. You'd have the 6-membered ring, okay, with the nitrogen in it here. Nitrogen, hydrogen. Then you have 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons, right? 1, 2, 3, 4. And then you'd have your carbonyl on here, your aldehyde, like that. And so again, you would treat that with a catalytic amount of acid and sodium cyanoborohydride. Give me a thumbs up if you follow me just on the concept. Okay, I know that this is organic chemistry too. You might think, well, I'm going to need a little time to try it on my own, but I can do it. Okay, cool. Yeah, it's not simple, that's for sure, but it's definitely doable. Definitely doable. Something I encourage everybody to do, since I did both ways for B, and it only did one way for C and D, I encourage you to try to find a second way for both C and D. Okay? All right. It says here that methamphetamine, which is crystal meth, is used in some formulations for the treatment of ADD and can be prepared by reductive amination using phenol acetone and methylamine. Draw the structure of methamphetamine. And I had it on a slide earlier today, so I kind of gave it away. But we're going to start with phenol acetone. So everybody knows the structure of acetone. That's acetone. All you have to do is throw a phenol on the side. There you go. There's phenol acetone. And then we treat that with methylamine. So methylamine is just CH3 NH2. So there's our ketone and there's our amine. If we treat that with a catalytic amount of acid and sodium cyanoborohydride, we can even draw the imine that results just for fun. So the imine is going to be this time it's a real intermediate. It's not isolated, but it's going to look like this, okay? That would be the intermediate. And then, of course, the sodium cyanoborohydride is going to reduce that to methamphetamine, which is going to look just like this. And as I told you, the drug is racemic, right? The drug that people take. And there you go. So this is methamphetamine. Nothing to it. All right. Now you're thinking, where can I get some phenol acetone and methylamine? I'm joking. All right. But if you've seen Breaking Bad, I think there's a part where they're trying to get some phenol acetone somewhere or something. I don't remember the whole show, but I think there was something about that at one point. Anyhow, so what have we learned? What have we learned besides, up until the points about physical properties, what have we learned about synthesis? We've learned there's 3 different ways to make a primary amine. I know there's another. I know you can do it with cyanide too. The difference is when you use cyanide, you add a carbon, right? Because cyanide has a carbon in it. So leaving cyanide out, what have we learned that's new? We learned the Gabriel synthesis using potassium phthalimide, which of course you can make from phthalimide and sodium hydroxide. So first step is an SN2, right? You do the SN2 and then you treat it with hydrazine. Okay, that works. We learned that you can use sodium azide. Okay, so the first step is an SN2 again. And then you can reduce that with hydrogenation, for example. Or, let's write in here, or lithium aluminum hydride followed by water. Okay, that works too. And then we talked about reductive amination. And the crazy thing about reductive amination is that it can be used to make a primary amine. Sure, you can definitely do that. But reductive amination can be also used to make a secondary or a tertiary amine. And then I said a tertiary amine, even that can do a runaway reaction to make a quaternary ammonium salt, right? You can end up making a quat, okay? Quaternary ammonium salt. So just by an alkylation reaction, that gives you all these different ways to make amines. Gabriel synthesis, azide synthesis, reductive amination can all be used to make primary amines. Then you can use reductive amination to make a secondary or a tertiary amine. So these are, the methods that we have to make amines. So that in mind, I want to take a quick peek at this question here. I don't do a lot of these questions in our book where he only gives you one possibility of a starting material, but he likes these kind of questions. It says, using only ammonia, only place you can get nitrogen, show how you would prepare each of the following amines. I mean, I guess the easiest way would be to start with a reductive amination. I chose, and I already did this one before class, I chose to make this part of the molecule first. So I chose to make ethylamine to start with. So that means I would start with acetaldehyde, like that. I would take it, treat it with ammonia, a catalytic amount of acid, and sodium cyanoborohydride, so NaBH3CN, and that would give me the desired amine. So then all I want to do is add all of these carbons over here. So I can just use an aldehyde again. So I'll take this molecule and I'll treat it with this guy, like this, catalytic amount of acid, like that, and sodium cyano, son of a gun, I keep doing that. Sodium cyanoborohydride, and that's going to give you the desired product, just like that. That would work perfectly well. I'm going to go over to a blank document to do the last one, so give me 2 shakes of a lamb's tail here. Find some space to do the question. So the next one, this is again 22.16, and this is B. If you want to make cyclopentanamine, which is this thing here, well, I would think about making this from a reductive amination, right? And starting with cyclopentanone, right? Because if I start with cyclopentanone, all I have to do is treat this with ammonia, catalytic amount of acid, sodium cyanoborohydride, like that, and that's going to give me my desired product. And then in C, you have N,N-dimethyl cyclopentanamine. So we have this compound. It's like this thing won't go away. There we go. But now we've got two methyl groups. So I mean, you could either break this bond here, okay, and then you could start with formaldehyde. So you'd start with formaldehyde, so just one carbon. Then you would treat it with this compound where you have a methyl and the cyclopentyl group, catalytic amount of acid, and sodium cyanoborohydride. And that would give you the product. Okay. Or the other option would be to break this bond here, in which case you would start with cyclopentanone. Okay. Then you would treat it with dimethylamine, a catalytic amount of acid, and sodium cyanoborohydride. So you can now see why this reaction is so great. Okay, because you can make disconnections at all kinds of different spots to make these different compounds. So a really, really useful reaction.